This data represents the fluctuating hormone levels of human reproduction. Mapping the underlying chemical logic requires looking into the timing of the system itself. The menstrual cycle encompasses two concurrent tracks, visualized here as concentric circles on a 28-day timeline. The ovarian cycle focuses on egg maturation, while the uterine cycle prepares the endometrial lining. The hypothalamus-pituitary-gonadal axis keeps both in perfect temporal sync. The coordination of these two organs relies on this shared schedule, driven by chemical signals, that ensure the uterine environment is ready at the exact moment the ovary releases an egg. Day 1 marks the beginning of this synchronized timeline. In the uterine cycle, this is the menstrual flow phase, where the endometrium sheds its lining. Concurrently, the ovarian cycle enters the follicular phase, where a protective housing for an egg cell, the follicle, begins to grow. As the tracker advances past day 5, the anatomical priorities of both organs shift. The uterus enters the proliferative phase, rebuilding the endometrium and filling it with blood vessels to nourish a potential fertilized egg. Because the ovary and uterus are physically separate, their internal timelines would drift without a shared signaling network, preventing a fertilized egg from ever finding a prepared environment. This coordination is driven by the HPG axis, a hierarchical control network that starts in the brain. The hypothalamus initiates the cascade by secreting gonadotropin-releasing hormone, or GnRH. This stimulates the anterior pituitary to release two signaling molecules, follicle-stimulating hormone, or FSH, and luteinizing hormone, known as LH. FSH acts directly on the ovaries, stimulating the follicles to physically expand as they develop the egg. As these follicles grow, they begin secreting a form of estrogen called estradiol back into the bloodstream. At low levels, this estradiol exerts negative feedback on the brain, inhibiting the secretion of GnRH and keeping FSH and LH levels low. This feedback loop acts as a systemic brake, ensuring the body doesn't overstimulate the ovaries and exhaust its follicular reserves. This chart shows how hormone levels shift over time. As a dominant follicle matures, it produces a steady increase in estradiol, moving the concentration towards this threshold. While the system is currently under negative feedback, which suppresses the brain, it must eventually trigger the high-energy event of ovulation. This shift depends on the biphasic nature of estradiol. Low concentrations inhibit the brain, but once estradiol crosses a critical high-concentration threshold, the effect on the brain reverses. At this high concentration, the system flips into positive feedback, where estradiol now stimulates the brain nodes rather than suppressing them. This causes the hypothalamus to suddenly increase its secretion of GnRH. The surge in GnRH forces the pituitary to release a massive spike of luteinizing hormone, a phenomenon called the LH surge. This LH surge occurs around day 14 and causes the dominant follicle to rupture, releasing the egg from the ovary. Using a single molecule as both the inhibitor and the trigger creates a self-regulating transition point between the growth phase and ovulation. Following ovulation, the timeline enters the second half of the cycle, spanning days 15 to 28. In the ovarian cycle, the remains of the ruptured follicle transform into a glandular structure called the corpus luteum. This structure begins secreting a new hormone, progesterone. Progesterone acts on the uterine cycle, driving the secretory phase. Progesterone's role is maintenance. It keeps the uterine lining stable and nutrient-rich, preparing it to support a fertilized egg. High levels of both estradiol and progesterone now exert strong negative feedback on the brain, effectively shutting down the release of FSH and LH. This shutdown prevents any new follicles from developing while the system waits to see if a pregnancy occurs. The 28-day cycle is a repeating system that will degrade and reset unless it receives a specific signal to continue. If no egg is fertilized, the corpus luteum begins to break down. As it decays, the levels of estradiol and progesterone in the bloodstream drop significantly. Without progesterone to maintain the lining, the endometrium breaks down and sheds, returning the system to day 1 of the uterine cycle. This hormone drop also removes the negative feedback brake from the brain, allowing the hypothalamus to restart the cycle. A different outcome occurs if a fertilized egg implants in the uterus. The implanted embryo begins releasing its own unique hormone, human chorionic gonadotropin, or HCG. This hormone acts as a signal to keep the corpus luteum active, maintaining progesterone levels and keeping the uterine lining intact. The cycle functions as a biological oscillator, a repeating sequence of feedback and concentration shifts that resets its internal clock until the signals of a pregnancy override the system.